Okay, fantastic. So my name is Juan Ulloa. Um, I come from a engineering background, so I'm an electronics engineer. But during my career, I wanted to develop tools for conservation. So for the PhD, I went to the Natural History Museum, where I met Camille, and where I study how to adopt all these tools that were developing from the engineering field to analyze soundscapes. And it's during this process that we develop Scikit-Math. And so this is, of course, a collaborative project that we developed also with Sylvain Aubert, that works at the Natural History Museum, with Juan Felipe Latorre, who was a student at the National University in Colombia, and with Thierry Aubin and Jérôme Sueur, who were my advisors during my PhD. So this was between 2014 and 2018, where this story begins. So as you all know, we have these passive acoustic sensors that we use for ecology and conservation research, and we can program them and automate the data collection. This is a fantastic tool. They can remain in the field during, collecting data for months and even years. And of course, this is a cost-efficient method to sample the acoustic environment. Yeah, and for example, this is the kind of information we get that I usually do this kind of visualization where you have from midnight to 6 a.m. to 6 p.m. and again to midnight. This is a spectrum from 0 to 48 kilohertz. This was recorded in the tropical forest. So you have lots of different small signals. I know that this is small, but what I want you to show is that we do not leave this for one day, but for many days. And of course, there's a lot of information here that we want to grasp, but this is the major bottleneck that we have right now. So processing the avalanche of audio recording is still challenging and represents nowadays a major bottleneck that slows down its application in ecology and conservation. And this is where this is what I was working on during my PhD. And during this PhD, we developed a particular kind of analysis that used bidimensional wavelet analysis and unsupervised learning. And we call this the multi-resolution analysis of acoustic diversity. And we use this kind of analysis to estimate the acoustic diversity in tropical soundscape. This was in 2016, more or less. We published this in Ecological Indicator, and this was developed in MATLAB because MATLAB has some very nice tools, but it has a problem that MATLAB is paid. So I was also wondering, so I'm developing all this kind of stuff in MATLAB. Right now I have a license to use MATLAB because it's the university license. But once I finish, what will I do? I need to be able to use this kind of analysis. So we were also looking to open source solutions, because open source solutions also facilitate the reproducible researching for science, which is very important. You can democratize the access to state-of-the-art developments. Of course, it promotes and facilitates collaborative research. And since the code is open, it gives you flexibility to customize all these developments to new scenarios. And so we would look for these open source solutions. For example, an open source solution that I'm quite sure that you most of all most of you have used is Audacity, which is a great tool to listen to and scan audio files manually. Looking for these open source solutions, we went first to R, where, as you might know, you have C-Wave to analyze the data, the audio, Warbler, and Monitor, just to name a few of them. We look in R if we can translate the code, but still we were lacking some major packages for signal processing. So we keep looking and we say, okay, there's Python. And what we realized is that Python offers a very suitable environment for scientific computing because it has lots of different signal processing tools and also pattern recognition tools. I'm not sure how familiar you are with Python, but just to let you understand, for those of you that only use R, Python for scientific computing is based on these main packages. You have NumPy, which is for matrices computation. You have also matplotlib, which it's used for plotting graphs. You have on top of this, you have SciPy that has lots of different tools. And associated with SciPy, you have the scikits that are scientific kits for scientific computing. And you have also pandas, which lets you use all the data frames, which makes very familiar. If you come from R, you can use this same kind of structure, which are very useful for our research. So looking at Python, we said, I think we have something nice to work. We have all the tools that we need to build this multi-resolution analysis. And we also were looking a place where this analysis will grow. And this is just maybe a take-home message, is that Python is growing very rapidly and constantly. This is a publication from the Institute of Electrical, and Electronics Institute. And it says that Python's, I'm just, sorry, totally. It says, learn Python. That's the biggest takeaway we can give you from its continued dominance of IEEE Spectrum's annual interactive ranking of the top programming languages. So this comes from the engineering field, and it's a very known magazine that makes this kind of ranking, and Python is being used more and more. So all the major technological developments are made in Python. So we found that Python was a very suitable place to develop this toolbox. And here we present scikit-math, a toolbox for quantitative soundscape analysis in Python. We wanted to develop math, but also different kinds of analysis that we were using in the lab. So we made some design principles. We wanted a flat package layout to facilitate the transition for R and MATLAB users. We did not want to use complicated objects or anything like that, something very flat and simple to use. We follow the PEP8 coding style, which is a standard for Python. We worked hard on a comprehensive online documentation to let people understand how to use math, and also a place where people can learn how to analyze these audio recordings. We also work to build a modular package with interchangeable modules that give flexibility in the analysis. And of course, we deliver an open source license that lets you use scikit-math for commercial uses if you want. So these are the main models that we have developed for now. We have the first module, and this follows like the standard analysis workflow. We have the sound module that lets you load and pre-process the audio. For example, you load the data and you want to resample the data, you want to trim the data, stuff like that. Then usually you might want to find some regions of interest. Sometimes you are looking for a species of interest. So you want to look for regions with high density of energy. So this module gives you all the tools to make this. And then you can compute temporal and spectral descriptors. That is, what is the main the peak frequency, what is the distribution of this frequency, what is the length of the audio recording. We also have here all these acoustic indices. And this is a development that has been led by Sylvain Aupert. We also have these modules that lets you link the audio recording to physical acoustic properties of the environment. That is to estimate the sound pressure level and also compute the detection distance. This active space module is being released during this month and next month. So let's look a little bit on these modules. So the sound module, for example, as I said, you can load very easily. This is a one-line code. You load this recording that's called Spinetail. It has a little bit less than 20 seconds, and you can visualize it. This is the amplitude, the waveform, the standard waveform. You can compute the envelope, you can compute the spectrum, and you can compute the spectrogram very easily. And if you come from R, you will notice that, for example, plotting a spectrogram is very, very fast in MATLAB. Then, once you load your data, you might want to find some regions of interest. And we have very simple tools. For example, to make a temporal segmentation in 1D, we have a simple wavelet, a detector based on wavelet. So you just have to give the temporal and frequency parameters, and it will find the main patterns that match these two features. This is a very simple detector. We have a detector that it's a little bit more complex that uses spectrotemporal segmentation, and this begins to be a little bit more interesting. For example, here you have the spectrogram. We use different tools from image processing to have a mask of this spectrogram, and from this you can have spectrotemporal regions of interest. And then after this, you can, of course, compute the features. That is the next model that we have. If you're working on soundscape patterns or acoustic community patterns, we wrote more than 50 of the most popular acoustic indices. So you can have these nice patterns of the soundscape during the hour. And we also have this that is based on the multi-resolution analysis, a 2D wavelet analysis that can compute the shape and the texture of the spectrogram. I've been using this quite often to detect and classify sounds of interest using whether supervised learning or unsupervised learning. So how this works is you can make all this kind of filters. All this you can compute it in 2 lines of code. You make this filter, and then you process the spectrogram with these filters, which gives you this representation. How you read this? You have the scale in the x-axis and the direction in the y-axis. So this is telling you that you have a lot of small vertical information. This is the texture vertical, and also a little bit vertical, but with some inclination. This is why you have some grain, some high coefficients here. And on top of that, you also have the main shape that is kind of a horizontal trill, because this is a complex sound which comes with this texture and this main shape. And this is why you have a higher coefficient here. And finally, you have also this model that's called the sound pressure level, or SPL, which you can use it to estimate the sound pressure level of acoustic events. So you can transform your raw data into decibels, sound pressure levels, and also to continuous sound pressure levels, or LEC. This can give you estimates in time and frequency. And what it requires is the recording settings and the recording parameters. For example, the microphone sensitivity, the gain, the peak-to-peak voltage of the ADC system. Yes. And you can have this kind of representation where not only you have the information on the time domain, but also on the frequential domain that can be very useful. And this can be linked to the physical attributes of the environment, that I think is very important for us to begin this kind of analysis, to be able to compare what is happening in our different sites. So where is all this code hosted? It's hosted on GitHub. I'm not sure if all of you know GitHub, but you have all the information here. So you can see all this. These are the main modules: feature, ROIS, sound, SPL, and this is utilities for plotting and etc. And if you look at sound, you have all the functions here. This is open source code. And something interesting about GitHub is that you can, once you're using this, you might find maybe some issues. You might want to develop new features, so you can always use this place here to publish the issues that you have, so we can improve our package, and you can make some pull requests to make some of your contributions. And this is what I was also telling you about the documentation. So we worked very hard to make a comprehensive documentation, to make this very accessible to everyone. So this is also hosted in GitHub. And you have here the installation instructions, which are, if you have Python, it's very easy. You just have to type pipe install scikit-math, and there you go. If you want the development installation, it's a little bit harder, but it's also very simple. And for example, we have the quick start, where you can learn how to use it very easily. And here are all the functions that I was talking about. And you have a complete information on how to use this function. And also we wrote some example for each of these functions. So we wanted to make this very accessible. And finally, also we have an example gallery that we're making bigger. Also, this is a place where you can contribute. For example, I was telling you about simple audio segmentation. Here you have all the information. We try to explain as much as we can how you use it, why you use it, and you can find here how to detect these regions of interest. So I hope this will be useful information for you that are beginning to learn Python and begin to learn scikit-math. Also, we made this publication last year where you have more detailed information about the package, how we design it, what are the purposes. This was published in Methods in Ecology and Evolution. And for the installation, as I said, it's very simple. You just type pip install scikit-math. And if you have scikit-math, if you want to upgrade, pip install upgrade scikit-math. This is because it's hosted in the Python package index, which is the main repository of Python. And this made things very easy to distribute. And we're working right now on a new version, that's the version 1.3, which will be released in next month, where we will add this active distance module. We also will have a wrapper to download files from Xenocanto. So you just have to type, okay, I want sounds from this species and located in Colombia during 2020. And you will be able to download all this data with a simple line of code. We also are implementing some functionalities to load manual annotation from Audacity and Raven, and we're making some small improvements. The perspective of this are, and I also take home message. I really think if you're really into passive acoustic monitoring, if you can, R is very useful for ecological analysis, but if you want to analyze raw audio data, Python offers a very suitable environment for this quantitative analysis. And we hope that this development also opens new links to other Python libraries. So you're just beginning to use Python, you use scikit-math, and you will understand that you have a bunch of other modules, very, very interesting, such as scikit-learn, scikit-image, that lets you do some very advanced signal processing and pattern recognition tools. And you also have TensorFlow and PyTorch for those of you that use deep learning for your analysis. We invite you to become a contributor. So this is a collaborative effort. You can just, for example, if you use scikit-math, you find issues, just submit the issues through GitHub. You can also submit new features. You can write to us and say, okay, I think this would be very nice to implement. And you're more than welcome to add some complementary functions or modules to scikit-math. This is very modular, so new improvements are welcome. We think that this is a community effort. We can also make a community effort to develop an ecosystem for open source packages for bioacoustic and ecoacoustic research. And we think that this is one of the main steps that we want to look forward to make really improve this collaborative research, to exchange new ideas. And we are sure that this development of scikit-math gives the opportunity to create synergies between the large community of researchers that seeks to explore, understand, and preserve the acoustic diversity of ecological systems. Thank you very much.
Thank you, Juan. We have already a lot of comments and questions in the chat. So Kali asked if there was an analog for R, but I guess you kind of presented some of the packages that are available for R, so that you read my mind. Renata Sousa Lima, would you like to ask a question? If you unmute yourself.
Yes. Hi, everyone. Can you hear me?
Yes, we can hear you.
So this is great one. I was wondering if you think that first part of your algorithm can serve for the mounting amount of acoustic libraries there are in development around the world. If you think this is something that can be implemented or is already implemented, like, you know, naming and archiving and maybe sharing. Any thoughts?
Yes, I'm not sure if I understood the question. Are you talking about functionalities to manage the data that we are collecting?
Yes, exactly. Functionalities that will allow a library to quickly organize the data and the metadata associated with the archives, with the sound archives.
I think it's yes. What's nice about, I'm not sure if what I'm going to say is correct or not, but I think, for example, the main difference between R and Python is that R was designed for statistical computing. It has one purpose and it expanded very fast to other purposes, which is really nice. But Python was developed for general purpose programming. So you can make all these different kind of stuff, approaches of using, of consulting libraries and managing metadata. I'm sure you can use it, but we should, I don't know, I'm interested in what you're saying, and if you can expand a little bit more of which functionalities you need, and think about if these are the functionalities that other people really want, and we can really sit down and discuss how to implement this in Scikit-Math. But yes, this is the idea, to make other functionalities for the community.
Sounds great. Thank you. Yes, let's keep talking about this and see what we can do together to plow forward. Thank you so much.
You have my email
yes.
here, so you can write directly to me and we can continue discussing. Thank you for your question.
Thank you.
Okay. Thanks. Next, we had Kali asking about the SPL analysis. Do you want to unmute, Kali?
Yeah. Sorry, I had like 4 questions at different points, so I apologize for that. This one was about, in the SPL analysis, you mentioned some parameters that I have like literally never heard of, like the voltage of ADC. I don't even know what ADC is. Is there like is that like in metadata? Are all of those parameters things you can pull out of like the metadata, or is that something you have to do through like collaboration or calibration, like experiments or something?
So, okay, yes, let me clarify a couple of things. So if you really need like a calibrated measurement, you need a sound pressure level specific tool. But still, with the audio recorder, since you're leaving a constant gain, you can make estimates, and fairly good estimates. And what do you need is that we're reading, in fact, what you're getting on the audio waveform are just voltages that you have to translate into this physical measurement. And that's why you need all the information about the recorder and yes, the recorder, mainly the recorder and the gain settings. And the ADC, it's not something complicated, it's just the analog to digital converter. And this is something that you can ask. For example, if you use the sound meter, you can ask to Wildlife Acoustics this specific these specificities of the recorders. And sometimes you can find them even in internet. For example, for the audio mode, you have it in the publication that they made, or you can search for the components and you find what is this specific thing. But it's not something complicated, but you really need to understand what are the main settings of your recorder.
Okay, great. That's super helpful. Thank you.
And the other 3 questions?
Well, one of them was about whether there, before you started talking about R, my first question was automatically, is there an analogous package in R? Because I feel like I run up against this all the time where like ecologists, you know, in like college are traditionally trained, our biostats classes are all in R. And then the people from the programming side, all their biostats classes are in Python. And then you end up with this like split later on down the line. And I've always just countered this with like collaborating with people who know Python and like they run the data and stuff. And I know that they're like R and Python are good at different things, but yeah, so I was just wondering if there was, like, I know of the R packages that you mentioned, but I didn't know if there was anything in the pipeline or about like making this, if it was even possible to like put it into an R package format, or if I just have to like suck it up and learn Python one of these days.
So yes, as I tried to explain, we first addressed to R because we knew that most of you use R for your analysis, but it was very complicated to find the basic libraries to make more advanced signal processing, such as wavelet analysis in 1D or 2D and other image processing techniques. So, and when we looked for Python, we saw that we had all that and much more. So we said, okay, we will have to work in Python and try to make this as easy to understand for people that use R. So the idea is also that it's a package that helps you use Python in a more easy way if you're using R. And that's why we develop all the documentation. And the older message is that I think if you're really going to keep working on this and you will have to analyze the recording, I think it's very useful to learn also Python. And you will need to know Python and R, and which is, because they are complementary in some ways. You don't have all these tools for ecological analysis in Python, which are already implemented in R. But if you know R, it will be much easier for you also to learn Python because the programming languages are very similar. The syntaxes changes a little bit, but it's not very difficult.
Okay, thank you. I've been told this by many people. Just have to one of these days, just have to dive in. I think that was it. So I don't want to take up the whole time.
Okay.
We can maybe take a couple more quick questions and then start the open discussion. So David, you had a question if you want to ask it.
Yeah, so I was just wondering if you'd done any sort of comparative benchmarking of so you mentioned you have a bunch of sort of acoustic parameter calculations. If you've done any comparative benchmarking of scikit-mad versus some of the other tools that are available to do the same thing? And like, are you guys a bunch faster, a bunch slower, about the same for like big batches of data?
So yes, we have like, but empirically, we haven't done any specific tests, but you just using it, you realize that, for example, as I said, just to compute the spectrogram, it goes very, very fast in Python. And you can also load very large objects in Python quite easily. And also, for example, to calculate the acoustic indices, we realized that we can easily parallelize this. And still, I'm sure that this can be done also with R. So just empirically, we noticed that it goes faster, but we haven't done any specific test to tell you, okay, it goes twice as fast or 3 times as fast as R. But just try it and let me know what you think of. And still also the other message is that this is not an algorithm that will solve you all your problems. No, this is a toolbox where you can get different tools to and customize it to analyze your data. Okay?
All right, thank you.